Let's talk about magnetic field. So a magnetic field is not only generated by magnet, it can also be generated by electric current. That's obviously possible. In conventionally, we know that we can actually have a magnet which has got a north pole and a south pole, and we will know that there will be some kind of magnetic field which will be there around it. Okay, but when we are talking about electromagnetism, we are more or less concentrating on the fact that how does a current carrying conductor actually create a magnetic field. So let's say we have got a current carrying conductor, and this is carrying, let's say, a current I. Okay, now what happens is, if you are basically keeping a magnetic compass near it, it's definitely going to show you some deflection. That means we can easily say that there is a magnetic field which is created at certain angle with respect to the current carrying wire. Okay, and magnetic field is also something which is directional. For example, if we take the same current in the opposite direction, we will see that the compass deflection will also get reversed. That means the direction of the magnetic field will actually depend in which the direction the current is flowing. So that's a very important factor. Okay, so a current carrying wire will actually produce a magnetic field around itself. In fact, the magnetic field that gets produced around the current carrying wire will be forming some kind of concentric loops. Okay, and from that we can actually find out the direction. Okay, so in general there are certain conventions that we should know. If there is something which is like this, this will actually give you a direction inwards. you know you can talk about the direction upwards and downwards, but what if the current is going into the plane of this board or coming out of the plane? Okay, for that these notations are helpful. This is inwards and this is outwards. So this may be magnetic field or even current also. Sometimes even the current is also represented by these kind of directions. Okay, and there are experiments being performed like the Oersted experiment. This experiment is actually a part of Oersted experiment. What he did was he actually considered this current carrying wire. Okay, and he placed a compass and he saw that there was a deflection, and he obviously concluded that if there is a current carrying wire, there will be a magnetic field generated around it. But there is one more observation that was done. If you have a current carrying wire and if you are having a charge which is static, so this charge is actually not moving. Okay, it is at rest. So if this charge is at rest, the charge will remain at rest. Okay, even if the current is flowing here, that means there is no force acting on it. No force on it. Okay, but on the other hand, if you're basically considering, let's say, a current I, and you have a charge which is moving, okay, then there will be a force acting on it. Now it might be thought that, okay, if there is no force, then the charge will move straight. Okay, but that does not happen. The charge actually gets deflected, maybe towards or away. Okay, depends on the direction of the current, but it deflected towards. That means whenever there is a moving charge, the current carrying wire will actually have an effect on it, and there will be a force which will be there. Okay, so due to some force, okay, the charge is getting deflected. Okay, so we know that if you basically have an electric field, okay, E, and if you are having a charge here Q, then QE is the force which is acting on it in an electric field. So here also we can see that there is definitely some kind of charge which is acting on it. Okay, so now what we are going to see is what happens. Okay, this force that we are talking about is actually because of the magnetic field. Okay, so now what we are going to do is we are going to analyze the law, which is very important, and based on that law we can actually write down a lot of calculations. Okay, we can do a lot of calculations here. Okay, other than that, I think unit is also important. So if we talk about the unit of magnetic field, so this is my magnetic field representation. We usually denote it by B, and we can write it down as Newton per ampere meter. Okay, so you know how much force we have by per unit current per unit distance. Okay, let's say x. So Newton per ampere meter, that is actually the idea behind the unit, or we also write it as Tesla. Okay, you can also write it down in terms of Weber. Weber is also a unit of magnetic field, Weber per meter square. Okay, so whenever you are getting values, you'll see most of the time these units are being used. Okay, now what we are going to do is we are going to find out the magnetic field at a certain point. Okay, we are going to find out the magnetic field at a certain point. For example, let's say we have got a current carrying loop, and what is the current or the magnetic field that is being provided in a nearby region. So determination of B. Okay. So we can find out the magnetic field anywhere due to a current carrying conductor or current carrying wire. Okay. Let's say I've got a current carrying wire which is I, and I have got some point P. Okay, which is at some let's say distance from the wire. Okay, it's from the center of the wire maybe. Okay, and if you are looking into a very small current carrying element, let's say this is a very small current carrying element, we have seen it before also that this shape is curved. So I really not concentrating on the length directly. First we are finding out what is the magnetic field at the point P due to a small current carrying element, and let's say this is making an angle theta with this current carrying element. Okay, so this is my direction, and this is my small current carrying element. Okay, so what we are going to do is we are going to find out what is the magnetic field due to this length dl, small element dl. Okay, the point P. So this is called the current carrying element. Okay, in order to do that we are going to use something which we call as Biot-Savarts law. A Biot-Savarts law does not have a proof as such. It is based on observation. Okay, but this is a very important law based on which we can find out the magnetic field for a number of shapes at any particular point. In fact, in order to know the direction also, we are going to use a rule which is called the right hand thumb rule. Okay, so what we are interested to find out is the magnetic field. Okay, intensity, we can say magnetic field intensity due to dl length, dl length of wire. So if you're finding out the magnetic field intensity due to a small length of the wire, that means you're going to find out a small magnetic field. If you're finding for the entire wire, you're going to find out the total magnetic field. So I'm finding out a small magnetic field. Okay. So if we just want to write down the vector form for this, it has got a vector form and a scalar form. Let me write down the vector form first, and I'll tell you how you can easily remember this. Okay. So if I write down the vector form, we can write it down as dB bar. Okay, is actually proportional to the components that are there. So you have to write down a proportionality constant. When we are writing down it for electricity, it's 1 by 4 pi epsilon naught. When we are writing it down for magnetism, it's mu divided by 4 pi, mu naught divided by 4 pi. Okay, and we can write it down as I, and it's a vector quantity, so I have to write down vector components here. dl cross r bar. Magnetic field is a vector quantity because it has got direction. So if you have dot product, it's not going to give you the direction because dot product will give you scalar. So we have a cross product here which is going to give me a vector divided by r cubed. Okay, this is the vector form. We can obviously write down the scalar form for this as well. Okay, and so for for that, what I can do is I can drop the direction and I can just write down the magnitude. So I can write it down as mu naught divided by 4 pi. This is I, and dl cross r can be written as dlr cross product. So it is sine of theta divided by r cubed. So cancel this out. This is r square. Okay. So this is my scalar form that we have. Okay. So if we want to write down the scalar form, although eventually we'll see that vector form and scalar form both can be used. Okay. This is mu naught divided by 4 pi into I dl sine theta by r square. This is actually easier to remember. I dl sine theta divided by r square. This is my scalar form. Okay, so this is my vector form of Biot-Savarts law. This is my scalar form of Biot-Savarts law. So it was observed, if you even if we we check some of our text, we do see that whatever is the magnetic field that is being produced at the point I is actually proportional to I. Obviously, how much current it's flowing through the wire, that will actually be based on that. Okay, this will also depend on what is the angle, okay, that point P is making if we draw a straight line to a small current carrying element. So obviously that will also depend on that, obviously. And it follows the inverse square law. We know that with distance the field intensity will get affected. So it actually follows the inverse square law. That is also true. And obviously it will depend on how much current carrying element you are considering here. So it will depend on what is the width of this dl, the length of this dl. Okay, so in this way we can actually combine all these I dl sine theta divided by r square, and we can actually get the scalar form. But we have a constant here, mu naught divided by 4 pi, so we should know what is the unit for this. Okay, we can in fact also know what is the unit of mu naught. But before that, let me just write down this value. Mu naught divided by 4 pi is equal to 10 to the power minus 7. Okay, we'll write down the unit later, but at this point of time, what is mu naught? Mu naught is permeability. Just like in electricity, we had 1 by 4 pi epsilon naught when we talk about charges. Here we are talking about the magnetic field, so it is permeability and not permittivity. Permittivity is epsilon naught, which is in free space. So this is permeability of the space. So that's the idea behind mu naught. Okay, we can easily write down what's the unit, because we know that the unit of B is Tesla, right? Into mu naught by 4 pi, we can take the unit of this. 4 pi is a constant, obviously. This is Tesla. Take this R here, so this would be meter square, right? This is I, so this would be ampere. To go down, and dl is again distance, so this is meter. Sine theta doesn't have any unit, so you can just cancel this out. So the unit for mu naught would be nothing but Tesla meter per ampere. Okay, so you can always guess what is the unit. So units and dimension plays a very important role here. Also the same thing as we did it in uh, charges case, that if you want to find out what is the relative permeability, you can just take the ratio of permeability in the medium divided by the permeability in free space. This will actually help us out to do our calculations for a complicated system. But anyway, let's see if we can do that. Okay, but this uh, dB that we actually have here, okay, you have to remember this. This is applicable on elemental charge. That means you're considering a very small element, elemental, okay, current, not charge, current. That means we have got a small current carrying element, ideal, and this is applicable for this. If you want to find out for the entire length of wire, we definitely have to do our integration. Okay, so that's here. And next thing which is important and which actually confuses us a lot, okay, this is the direction. Because you are basically going to consider a magnetic field which is actually a vector quantity. So if you want to find out the direction, you have to use certain laws. Okay, this is, let's say, b bar. Okay, and we know that this is actually given by this vector dl cross r bar. Okay, so if you remember that the product cross product rule, okay, a is equal to b cross c, if we say, okay, so that means this a is actually perpendicular to the plane containing b and c. Okay, so what happens is, if you're basically having a plane, okay, this is my b and this is my c, direction of a would be in a direction perpendicular to both b and c. Okay, so it's not that b and c will be perpendicular to each other, but a will be perpendicular to both b and c. Okay, so this is also the logic which works. But here what we are going to do is, there are two rules that we can use. One is the screw rule, Screw rule means if you're taking a screwdriver and you have got a screw, right? Okay, you've got a screw and you're trying to put it in. Okay, maybe it's a wood and you want to put in that screw inside. What you're going to do is you are going to take a screwdriver. Okay, you're going to take a screwdriver and going to rotate it. Okay, so you're going to rotate it either clockwise direction or anti-clockwise direction. Okay, and based on that you can actually get what is the direction of the field. Okay, so what is the direction between dl and r will actually give you what is this direction of the magnetic field. But even better than that, okay, so for example, let's see, I'll show you this. Maybe I can have, this is my dl and this is my r. dl r. So if you're going from DL to R, you're going to move the screw like this. Okay, going to move the screw like this, or you're going to rotate the screw like this. So this is in clockwise direction. So if I'm rotating something in the clockwise, direction, this is, the screw is going to go inside. The screw is going to go inside. So that means this would be the direction of the magnetic field. Okay, this is what the screw rule says. Okay, but there is a better technique. Okay, there is a better technique to do it, and you'll see that most of the books, or even if you are using it, you'll see that this is much more simpler. The better technique is the right hand thumb rule. Right hand thumb rule. So it obviously says that you are going to use the thumb of your right hand, and that will actually give you the direction of the magnetic field. Okay, so let me take a simple case and we are going to observe it later. Okay, we're going to use it also later. So let me say I've got the same current carrying element. It is carrying a current I, and I want to find out this magnetic field direction at the point P, and I want to find out the magnetic field direction at the point Q. Now, what does right hand thumb rule says, that if you're actually going to find out the magnetic field on the left or the right, okay, if you're going to find out the magnetic field on the right or the left, you can actually take your thumb. Okay, now this is a bit difficult to show you on screen, but what happens is you can actually take your thumb, a thumb of your right hand. Okay, and then you are going to take your other fingers. Okay, not that good at drawing, but let's see. Okay, so we have got taken this other finger, and we are going to put it towards this P, and we are going to curl our finger. We are going to curl our finger. We are going to curl our finger. And we are going to see at this particular point in which direction my fingers are getting curled. This is my right hand, okay? Right hand, not the left hand, right hand. So this is my thumb. Thumb is pointing in the direction of the current. So this is the rule here. Thumb in current direction. Current direction. And then the finger is going to get curled. Okay, the curled finger is, you can practice it also to any kind of system of B. So you see this is going inwards, so at this particular point P, this is inwards. Now we want to find out what is the direction in Q. Now you see this is going inwards. Now you curl it, and you're going to curl your finger and going to come out like this. So when you come on the other side of the wire, it will be seen, or it will be observed, that my fingers are coming out of the plate. So that means on this side the direction of this is coming out of the plane of the paper. That's it. That's the rule. Okay, if you know this rule, if you understand this rule, we can actually find out the direction of the magnetic field at any particular point. Okay, we can actually check and do it. Okay, so for practice, what we can do is we can consider different kinds of system and find out what is the direction of the field. Okay, for understanding purpose, let me just give you one or two exercises here. So if we say this, maybe I have a current. Okay, I have a current in this direction. This direction, this is my current. I can use my finger. Okay, and I have to find out what is the field at this particular point. Okay, this may be one problem. Okay, let me take one more. We can have a current flowing in this direction. Okay, and let's say I want to find out what is the field at this particular point, the direction of the field at this particular point. Okay, and number three, as I said, it's not that this cross and dot will always represent uh, current. It may also represent sorry, magnetic field. It can also represent current. So let's say this is dot product, this is dot, which means that it is going into the plane of the paper. So this is the direction of the current. You have to find out the direction of the magnetic field at this particular point. This is going into the plane of the paper, the current. Okay, we have to find out what is field at this particular point. Similarly, we can also say that this is coming out of the plane. This is I, and we have to find out what is the direction of magnetic field. Always remember, whatever may be the direction of the current, the magnetic field will be a perpendicular direction. So, if we are talking about on this plane, the current is on this plane or on this plane, the magnetic field, in order to be perpendicular to the plane, has either to come out of the plane of the board or go into the plane of the board. That is the only direction possible for being perpendicular. Here, the current is going in. So that means the current or the magnetic field direction would be on the plane. So it will be along the x-axis or the y-axis, not along the z-axis. Here also, the current is along the z-axis coming out. So the field has to be in the x-axis or in the y-axis. Okay. So think about this and try to find out the answer for this, because when you actually have these kind of questions in exam, you have to more or less don't have to explain much. You have to just show the diagram, or at least you have to choose the correct option. So option might be inwards, outwards, towards right, towards left, up, down, x plane, y plane, and so on. Okay, these kind of options might be given. So what happens is, if you're taking your right hand thumb, okay, you can think about it. You're taking your right hand thumb, and you are going to uh, your right hand thumb would be like this, right? So your other fingers will be like in this direction, in this direction. So that means if you're curling them, you are going to curl them in this direction. So on the, if it was on this side, it would have been inwards, but it is on other side of P. So that means this is going to be like this. So the direction at P would be outwards. That's important. Okay, look at this case. Now this is the current is flowing in the opposite direction. So that means you have to hold it like this. You can check it with your thumb. Hold it like this, and you will see that your fingers are going like this. Your right hand finger, and it is going to curl like this and going to come out of the plane on the other side. So this one will also be outwards. Just think about right hand. Don't use your left hand. Then only it's going to work outwards. Here also, you see, this is going into the plane of the paper. Okay, so if you take your right hand and go into the plane of the paper, okay, go into the plane of the paper, and when you check it, you'll see that you have to see what is this. This is my R, and if you're taking about this going into the plane of the paper, take your right hand. You're going to see that uh, the field is going to be in this direction. So you have to check it with your hand and see what will be the direction of the field. Similarly, this is going yeah, sorry, this one was inwards, this is going coming outwards. So if it's outward, it will be just opposite. The field will be in this direction. Okay, obviously making an angle of 90 degree with this uh, field. Okay, or with the current flow of current. So you have to use your thumb carefully, so that you are able to do this problem. Okay, so you can have these kind of problems again and again. You'll see that you'll be able to solve it. Okay, now what we are going to do is, we are going to find out the field due to a current carrying wire. Okay, let's do it. So magnetic field. So you have to find out magnetic field at different positions at different points, but due to sorry, current carrying wire. So it's always important that you look into the structure. If it's a wire, how you are going to find it out, and if you know it for a wire, you can easily find it out for different like circles, triangles, squares, and so on. Okay, we can go actually divide it into different parts and then find it out. So if you want to find out a current magnetic field due to a current carrying wire, this current carrying wire, let's imagine it to be straight now. Okay, it's a straight current carrying wire, and remember that it length might be infinite as well. Infinite means it's going to be very large length. Okay, so let's say I want to find out what is the magnetic field at point P. Okay, and this particular point P, okay, is at a perpendicular distance. Remember this term, it is at a perpendicular distance A. So every time we want to find out the length of, I mean the field at point P due to the current carrying wire, we have to consider a perpendicular distance. That's very important. And apart from that, let's say it's a finite wire. Let's say it's making certain angles with both these directions. Okay, so let's say the direction of current is this. We have already defined this, and let's say this angle is phi 1 and this angle is phi 2. Phi 1 and phi 2 are in opposite directions. That's important. Okay, and you know let me why not extend this way here a bit more. Okay, so maybe we can actually find out at this particular point due to a particular length of the wire. Okay, so what I'm going to do is this. Okay, let me just remodify the diagram a bit more. So this is my entire length of the wire. Okay, this is the entire length of the wire, and let's say we are basically considering a small current carrying element. Let me just do it a bit more clear this way. Okay, so in general what we do is that if you want to find out for the entire length, what we do is we actually find out what is the magnetic field due to a small element. So let's say this small element is dl and this is located here. Okay, and we are actually drawing this, and this is my distance, perpendicular distance. So this is my a. Okay, and you can see there are two angles that are being made. Let's say this small current carrying element that we have is making an angle theta, and the end of the wire is making an angle of phi 2. Okay, the end of the wire is making an angle of phi 2. Okay, and let's say this current carrying element, let me say that this is at a distance L from the center. Okay, so what we are seeing is that we have got a long current carrying wire, and we want to find out the magnetic field at point P. For that, what we do is we first consider a very small current carrying element, because in Biot-Savart law that we know that we have to first consider a small current carrying element. We want to find out the field because of that, and then obviously for finding out the entire field we can do our integration. Okay, there are two observations that are being done here. Okay, so let's just write down this note here. Okay, the first thing is A that we have is perpendicular distance. Please remember this. We are going to use this logic later. Okay, that's the first observation. And second, we can see phi 1 and phi 2 are in opposite direction. Are in opposite direction. Very important. Okay, phi 1 is going extending in this direction, phi 2 is extending in this particular direction. Okay, so now what we can do is we can actually find out what is my magnetic field. Let's try to find out what is my magnetic field at P due to element L. Okay, so magnetic field at P due to dl. So we can use our Biot-Savarts law here. Very simple. We can simply say this is dB is equal to mu naught divided by 4 pi, okay, into idl by r square, idl divided by r square, into sine of theta. Okay, so you have to know what is this theta. So you can see that this is actually making an angle of 90 degree. Okay, so obviously this angle that we have, this theta, okay, this is nothing but 90 minus theta. And if you recall, if you're talking about the Biot-Savarts law, and if you know what is our theta, if you check here, this was our theta, right? If this is point P, we're joining the line, whatever angle it makes is theta. So if you check here the diagram, this is my theta, this is my 90 degree, so this has to be 90 minus theta, so this would be nothing but sine of 90 minus theta. That's the logic, right? Obviously 90 minus theta. And what is sine of 90 minus theta? It is nothing but cos theta. Okay, so we can simply write it down as mu naught by 4 pi into I dl divided by r square. This is the application of Biot-Savarts law, so you can consider it to be a numerical. Okay, so this is I dl divided by r square cos of theta. This is cos of theta. Okay, now this is because of a small current carrying element. If you want to find out the entire magnetic field, obviously we have to integrate it. And if you look into these components, mu naught by 4 pi is a constant, I can take it out. Mu naught by 4 pi is a constant, I can take it out. I current is a constant. Okay, and then what happens is, r square, which is nothing but uh, okay, so r square we have it, right? Just a sec. So in our case we can see that what is r square we have not yet even found out, right? So this is our r, right? So if you look into the definition, or if you look into the diagram for Biot-Savarts law, this is our r. So we can write it down as r square. Let me just keep these things inside here. dl cos of theta. Okay, so we have it here. I is also constant, we can take it out later. Okay, but let's find out what are these components here. So first thing, what is cos theta? Okay, base by hypotenuse. So base here is a in this particular triangle, base is a and hypotenuse is r. Okay, cos theta is a by r. Okay, so that means from here we know what is r as well, a divided by cos of theta. Okay, we can also find out what is my dl from this. Very simple, we can just take out what is tan theta. So tan theta, if you consider this particular triangle, this is my length l. Okay, so perpendicular divided by base, right? So it is l divided by a. So l is equal to a tan of theta. Okay, that means we can find out what is my dl. We can do our differentiation, we can find out what is dl by d theta. Dl by d theta is equal to d theta of a tan theta, and d theta of tan theta is nothing but sec square theta. So from here we can find out what is my dl. Dl is equal to a sec square theta d theta. Okay, this is what we have here. So now what we can do is we can actually try replacing these quantities. Okay, first is mu naught divided by 4 pi into I divided by r square. So you see this is r, the distance that we have, and r is written as a by cos theta. So a is this distance, perpendicular distance, which is more or less a constant. So we can take it like a by cos theta. So let me just write it down first here, and then maybe we can take it out. 1 divided by r square. So r square is a square divided by cos square theta into dl. Dl is on top. Okay, so we can replace my dl. Dl is a sec square theta d theta. So I can write it down as a sec square theta d theta. Just get the maths here, that's it. Okay, a sec square theta d theta. Dl is done, and what is left is cos theta, cos of theta. Okay, so a and a square gets cancelled. This is sec square theta. 1 by cos square theta, here is also sec square theta. So that means this and this will actually get cancelled out, right? The square theta will also get cancelled out, so the things becomes more simplified right now. So we can write it down as mu naught by 4 pi into I divided by A is the perpendicular distance, which is constant, which is not changing. Integration, we are left out only with cos theta d theta. Okay, so this is for a small element, and if you're integrating it, we are going to get the entire magnetic field. Now if you go back and check the diagram, theta is only this particular portion. If I want to consider the entire wire, that means I have to start from this end, I have to start from this end and end here. So that means I have to go from phi 1 to phi 2 or phi 2 to phi 1. Okay, so phi 2 is in this direction, negative direction, and phi 1 is in the top direction. So what we can do is we can do it like this. Phi 2 is negative and phi 1 is positive. So if you look into the axis here, so we can just simply do our integration. That means we have to more or less put our limits. So this is minus of phi 2 to phi 1. And if we do this integration, we are going to cover the entire length of the wire as per the concept, right? So you're starting from here and going up to the total upward. So it is minus phi 2 because it's bottom of the x-axis, and then phi 1 of the x-axis, right? So what we can do is we can just simply do our integrations here. So this is mu naught I by 4 pi a, and cos theta, if you integrate it, it is sine theta. This is minus of phi 2 to phi 1, right? Further we can do it, so it's nothing but mu naught I by 4 pi a. Okay, upper limit is phi 1, so I can simply write it down as sine of phi 1, and then minus lower limit, but we do know that sine of minus theta is equal to minus sine theta. So that means that sine of minus phi 2 is minus sine phi 2. So minus minus will become plus, and this will be plus sine of phi 2. So this is the total magnetic field because of the wire, and this is a very important relation which can be used to solve a lot of problems. This itself is an application of Biot-Savarts law, but you'll see that if you remember this result, we can use it to find out the magnetic field at different points. Okay, so please remember this: A is the perpendicular distance, and phi 1 and phi 2 are actually measured in opposite direction, and based on that we can actually solve other problems as well. Okay, so we can do some numericals based on this if this formula is clear. Okay, so the formula is important. Let's write it down here. So this formula you have to remember: magnetic field due to a current carrying wire. We'll see the different shapes we can use it. Mu naught divided by 4 pi into sine of phi 1 plus sine of phi 2, or sine of theta 1 plus theta 2. It's just the two angles. If you remember the diagram, you can do it, right? So let's take one example here. So it's a simple example. Okay, let's start with a very simple example, and then we will look into more complicated problems here. So let's say I have basically got certain finite length, and there is a point P here. Okay, and this is my perpendicular distance. Okay, so these are the things that have been given here, and obviously the angles would be given. You can easily find out what is my magnetic field. So let's say this distance that we have is 10 meter. Okay, the angle here is, let's say, 45 degree. At the bottom, let's say it is 30 degree, and you're supposed to find out the magnetic field and the direction because of the current carrying wire, which is, let's say, taking a current I is equal to 2 amperes, but it's in the upward direction. So first thing, direction, you take your right hand rule, thumb rule, you hold it. Okay, hold it, uh, the thumb in the direction of the current, and curl your finger. You will see that the current is going inside. That means the finger curling is going inwards. Okay, so the direction is easy. I've already found out what's the direction. So whenever you are having a question, if you don't write down the direction for the magnetic field, your answer more or less would be incomplete. So that's important. So if you want to find out the magnetic field, I don't have to do so much calculation because I already know what is my formula. Okay, so mu naught divided by 4 pi is nothing but 10 to the power minus 7. Okay, let's not write down the unit right now, into I, which is the current, which is 2 amperes, divided by whatever is the perpendicular distance. So remember, this has to be a perpendicular distance. So this is 10, and this would be nothing but sine of 45 plus sine of 30. So this was simple, right? So if you do it, 10 minus 7, so 10 will go up, 10 to the power minus 8. So this is 2 into 10 to the power minus 8 into 1 by root 2, sine 30 is half. Okay, and you can do your calculations and see what is your answer. Whatever is the answer can be written in terms of Tesla or Weber per meter square. Okay, simple. Let's take one more example which is not as simple as this. This is number one. Let's take number two. Okay, here also we have to find out what is the magnetic field, but this time the shape is more or less different. So you can actually get these kind of problems. Okay, these kind of problems are more common because whatever I have shown here, it's nothing but direct example of or application of that formula that we have just now derived. Okay, so here we might have a current flowing in different direction. This is I. Let's say this is the current that is flowing. I, I, I. Okay, so once we have this direction of current here, we want to find out what is the magnetic field at this particular point P. Okay, so let's clarify the question here. P B due to entire loop, entire loop at P. That is what we actually want to find out. Okay, so if you look here, and this is, let's say, all the sides are equal because this is a square. That is what we are saying here. That means we can actually first find out what is the magnetic field at this particular point. Okay, because of this current carrying length. Okay, so we know, let's say the length is A. Okay, so, or maybe I can say the direction is given to be 2A. Let's say this entire length is 2A. 2A. Okay. So if you look into the geometry now, if this is 2A, this entire length, this is exactly at the center. So this length has to be A. So this length is there. This is the perpendicular distance, and obviously this is an equilateral triangle. So this, entire will be 90. Bisect it 45. Bisect it 45. So obviously this is going to be 45 degree. This is also going to be 45 degree. Okay. So if we now want to find out using this formula, the due to this is B naught is equal to mu naught I divided by 4 pi A into sine of phi 1 plus sine of phi 2, right? So now we know A is perpendicular distance, so already given. So I can write it down as mu naught divided by 4 pi into I divided by A. This is A. If this is 2A. If this is A, this would be A by 2, right? And so on. So maybe write it down as A, and then this would be sine of 45 plus sine of 45. So 2 times of sine of 45, and sine of 45 is 1 divided by root 2, right? So that means I can simply write it down as mu naught divided by 4 pi into I, right? Or 2I, right? Let's write it down as 2I. I'm not rationalizing right now. Divided by root 2A. So this is the magnetic field because of this. But if you look into the symmetry here, the same would be because of this also. The same would be because of this also. And there are four sides. This is 1, this is 2, this is 3, this is 4. So that means if you actually want to find out the total magnetic field here, okay, that means if you want to find out what is B, it would be nothing but because of the first, second length, third length, fourth length. But it's symmetric. You're going to get the same answer for all of them. So it is going to be 4 times of B1. So that means the answer is going to be mu naught divided by 4 pi into 8I 4 times 4 into 2 is 8 divided by root 2, and that would be your answer of the magnetic field. Okay, looking into the direction, I think it's again simple. If you look here and you draw your thumb, okay, if we have the current flowing in this direction, we can actually draw our thumb like this. Okay, take your right hand, okay, not the left hand. If you take your right hand, you'll see that your fingers will come in this direction and it's going to curve in this direction, so that means it's going to come out of the plate, come out of the plate. So that's going to be outwards. Okay, this side it would be in, on the other side it would be out. Then think about left and right. Okay, so if you're one more thing, if you are having like this, if you are going towards the left, it's right is going in. If towards the right, it's going to come out. So here also it's going to come out of the plane of the board. Sorry, come out, right? So dot, not cross, dot. That's it. So it's going to be this outwards. Check for all of them. You'll see every time it's going to come outwards. Okay. So based on this logic, we can actually find out the magnetic field for a number of system. Okay, maybe I can give you one more problem to think about. Okay, so in my next problem, let me consider a triangle. Let's say it's an equilateral triangle. Okay, it's an equilateral triangle. Okay, and you have a point P here. You're supposed to find out what is the magnetic field at this particular point P, which is nothing but more or less acting as a centroid. Okay, and this is an equilateral triangle, remember, and let's say the side is A, this is A, this is A, each side is equal to A. Equilateral triangle means all of these angles are more or less 60 degree. Okay, so what you have to do is you have to try to find it out. Okay, T at B. Okay, and let me give you the direction of current as well. Okay, let me just change it a bit. Maybe this side I'll take this time. This is I, this direction is I, and this direction is I. The sense is same. This is flowing in this clockwise direction. Previously I've given you anti-clockwise. Now this is clockwise direction. Okay. So the question is find B at B. Okay. Direction, I hope you can do it. Again the same thing. Okay. If you're considering the loop. Okay. This side, if you take the right hand rule, right hand thumb rule, you are going to see that if your thumb is like this, your fingers are going to be like this, right? So that means it's going to go inwards. So that's going to be the direction of the field. So let's not concentrate on the direction of the field right now. Let's just check for the magnitude of the magnetic field at point P. Okay, use the same rule and try to find it out. Stop today. So it's a simple, obviously this is an equilateral triangle, so we can just look into the different angles that are being made. If we're able to find it for one direction, we can able to find out for all the three. So we can just draw this, and this is our perpendicular distance, let's say. Okay, this perpendicular distance, maybe we can write it down as L, but L is unknown. We know the side of the angles, but side of the triangle, but not this direction or distance. This is 60 degrees, so this half the angle would be 30 degrees. And if it's a centroid, the angle that is subtended at the center is twice the angle subtended here. So that means this is going to be 60 degree. This is also going to be 60 degree. Correct. So that property of triangle we should actually know. 60 30 is 90, and this would be 90. This is 30. So we know it. Now the first thing is we have to know what is our perpendicular distance, right? So we can just find out what is tan of the angle, right? So if we talk about tan of the angle, maybe we can take tan 30. Okay, so tan 30 would be nothing but perpendicular, which is L, divided by base. Base is A by 2, right? A by 2. Because, okay, let me just make it a bit more clear. This is my A, entire length is A, so this is A by 2, and this is also A by 2. So we have it here, right? So in that way, we can actually find out what is my L. Tan 30 is 1 by root 3, and there is already a 2 there, so it will go on top. So I can find out what is my L. So it would be A, take it here, cross multiply by 2.3. So now I know what is my perpendicular distance, right? So this I can find out what is my magnetic field. B1 is equal to mu naught divided by 4 pi into. So that's why I said that you should know that what is the perpendicular distance, how you're going to find it out. That's very important. I divided by A by 2 root 3. Okay, that's my perpendicular distance. And then this side and this side making angle 60 degree on opposite directions. This is sine 60 degree plus sine 60 degree, right? So sine 60 is nothing but 1 by root 2, right? So we can do our calculation. So this is mu naught divided by 4 pi 2 root 3 into I divided by A. Okay, this is sine 60, sine 60. Okay, so it is 1 by root 2, 1 by root 2. So it is 2 divided by root 2, right? Sorry, I'm saying not 1 by root 2, it's 60, right? 60 is root 3 by 2. 60 is root 3 by 2. So root 3 by 2 plus 2, root 3 by 2. So it is 2 times of root 3 by 2. So this 2 and 2 will get cancelled. I'll get root 3. Root 3 is 2, 3. So that would be mu naught by 4 pi into 3 to say 6, 6i divided by a. So that's because of one direction, one side. So obviously, if you want to find out what is the B net, it's all symmetric here. So it is 3 times of whatever value we have. So if you have a multiple choice question, you can actually find out the magnetic field due to a circular current carrying loop. So maybe magnetic field due to circular loop. Now for doing this, simple, we can actually, let's say we have got a circular loop which is basically carrying some current, okay, and the current is flowing in circles. So that means at any particular point of time, the direction of the current will be tangential. Okay, this is something which we already know the concept. And let's say we are basically going to consider a small length dl. Okay, because if we remember the Biot-Savarts law says that dB is equal to mu naught by 4 pi I dl sine theta by r square. Okay, so that's our Biot-Savarts law. We are interested in finding out the entire magnetic field due to this current carrying loop. Okay, and if the current is flowing in this direction, we can use our right hand thumb rule and we can see that at any point, let's say we are considering and going to find out the magnetic field at the center, we are going to see that the field will always be pointing inwards. Okay, so we can find out what is the magnetic field at this particular point P due to this small element which is, let's say, at a distance a from the center of the loop. Okay, so if we consider that distance to be a, this r is general, let's say this is a from the center of the loop, so we can simply write it down as a square, right? So we can change it like this accordingly. But what is my sine theta? Sine theta is the direction between DL and A. Okay, sine theta is the direction between DL and A. Now you see this DL and current, they are in the same direction and A in is this direction. That means if you are considering a three-dimensional picture and if it's creating a tangent at any point according to geometry, this particular angle that we have between A and theta, okay, will be nothing but 90 degree, right? So if you remember, when we talked about the Biot-Savarts law, and we are going to find out the magnetic field at this particular point P, and we are drawing a line. This is the angle theta between the small current carrying element and the electrode. So if we look here also, if we look here, it is nothing but 90 degree. So that means I can simply write it down as mu naught by 4 pi into I dl. Sine 90 is 1 divided by a square. Okay, so this is my magnetic field, and this is obviously acting inwards, but this is because of this small current carrying element dl. I need it for the entire loop, so I can divide this loop into the small elements of dl and so on, and add them up. So mathematically speaking, we have to just do our integration. So that's how we can actually find out the total magnetic field. So if you just consider, you can find out the total magnetic field due to the circle, basically a circle of charge. So we can take this like this, and mu naught by 4 pi into I dl by a square, right? Now if you look here, more or less everything is a constant. Mu naught by 4 pi is obviously a constant, and current flowing in this circle is constant. This a is also constant because that's the radius of the circle, so this will remain constant. So this is a square. The only thing that I need to integrate is dn, and this is basically a closed loop. So that means if you take this length, it is going to form a circle, it's going to form a closed loop. Okay, so if we look here, this is nothing but the entire length by I by a square. And if we look into this entire length, that means we are talking about the circumference of the circle, and the circumference of the circle is 2 pi r. In our case, the radius is a, so I'll write it down as 2 pi a. So this is I by a square into 2 pi. We'll just do our standard cancellation. 2 it will become 2 pi, and pi will get cancelled, right? So that means the net magnetic field at the center due to a current carrying loop is nothing but mu naught by 2 into I divided by A. This is a very important relationship. If you can remember this, relationship, we can use it for a number of cases. Okay, uh, we can actually think about it in terms of angles. Okay, and find out the results. So let's just say we are talking about a semicircle. Okay, if we are basically considering a semicircle, that also can be done using this particular formula. Okay, and even this can be used for different kinds of structures. For example, let's say if you're basically considering a semicircle semicircle or semi hemisphere, that's a sphere, this is a semi hemisphere, we can say. Okay, so semicircle, so semicircle means half the circle, right? And we are having a point A here, sorry, P here, and we want to find out what is the magnitude. Same thing we are going to do. This is my dl, this is my direction of I, this is my 90 degree. That means if I write down the net magnetic field for the circle, it was mu naught I, sorry, mu naught I by A, mu naught by 2, right? So our result. Now this is for the entire circle. Now if you're basically considering it for this case, you know that this I by A came into the picture because we had the circumference as 2 pi A. Our circumference was 2 pi A. If you're considering a semicircle, that's half of that, right? Half of 2 pi A. So that means it will be the same calculation, only an additional half will come into the picture. Okay. Therefore, the V magnetic field because of the semicircle is half of mu naught by 2 into I by A. By knowing these formulas, we can actually solve a lot of problems. So let's try to know and remember these formulas as well. If you don't remember, you can try deriving it. That should also not be very difficult. Okay, but it is not necessary that you are always going to have a semicircle or a circle. Okay, it can be also in the form of a code. For example, something like this. Okay, if we have something like this which is only a part, okay, which is only a part, and let's say this angle is making theta, and I'm supposed to find out what is the magnetic field at this particular point. Okay, so this is more or less a code. Okay, so if you take that case here also, first thing we'll do dB. Okay, and the angle and everything becomes the same. It is 90 mu naught by 4 pi into I dl divided by a square. Okay, that will more or less remain the same. So that means if I want to find out what is my total b net, okay, we have to write it down as mu naught divided by 4 pi into I by a square integration of dl, right? But dl this time is, this is dl, this is dl, this is dl, this is dl. It's on the cone, right? It's not the entire circle, so we cannot directly use our formula, right? That will be a bit tricky. But if you look here, in this particular case, theta, okay, by definition is nothing but arc by radius, right? That is our formula, arc by radius. That means this distance is the arc, and this is my radius, and radius is a, take it from here, take it from here, from center to any other point, that will also be more or less a, right? So if you remember the definition of sine theta also, okay, it will be this divided by a. So if the theta is very small, we are talking about a small angle here, we can write it down as arc divided by radius. Okay, so this arc, we can consider it to be the entire length L, right, divided by A. So what will be my L? Entire length is A theta. So if the entire length, let be A theta. This integration of dl is talking about the entire length. So that means I can write it down as mu naught by 4 pi into I by A square into A theta. So I can cancel out this A here, and therefore for this particular case B net, we can write this down as mu naught by 4 pi into I theta divided by A. So theta is nothing but whatever is the angle that is subtended. But please remember, since we are not writing it down in terms of sine theta or cos theta, this has to be written in terms of radians. This has to be written in terms of radians. Okay, so if we talk about radians, we know that 2 pi is equal to 360 degree. So this is nothing but in radians, and this side it is in degree. So that means pi radian is equal to 180 degree. So if you look into that formula now again, for the arc, B net is equal to mu naught by 4 pi, easy to remember, I theta divided by A. You can remember this formula and think about the circle or the semicircle, and it should totally work. Okay, so if you're basically considering the circle here, if you're basically considering the circle here, that means the angle that is being subtended at the center is 360 degree. And what is 360 degree? 2 pi. So for circle, okay, if you're talking about the circle here, we can simply write it down as mu naught by 4 pi into I by A, and theta is 2 pi for the circle. So you can cancel this out. Cancel this out. I'll just have 2, which is nothing but mu naught I by 2A. Okay, if you're basically considering it for the semicircle, it would be nothing but mu naught divided by 4 pi into I by A into pi. Our semicircle is 180 degree, right? Only half the circle. 180 degree. Cancel out pi here. Okay, so this would be nothing but can be written as half mu naught I divided by 2a. 4 I've divided it to two parts. Okay, so let's check what was our for our circle. For the circle, our result was mu naught by 2 pi by 2 into I by a. We got mu naught I by 2 into a, and for semicircle it's half of mu naught I by 2a. For semicircle it's half of mu naught I by 2a. Okay, so that's how we can actually use this law of finding out these current. Okay, and mainly the Biot-Savarts law, very helpful to understand and get the logic of magnetic field due to a circular coil and so on. Okay, one more thing that is important, let's just get back to the Biot-Savarts law here. And we saw that this was our result. Okay, mu naught I by 4 pi into sine phi 1 plus sine phi 2. Okay, so if we redraw this picture, what we have is this. Okay, and this was our point P, and we are interested in finding out the magnetic field here. Okay, now imagine this wire that we have is not of finite length. We said it was of finite length L. Let's say it is of infinite length. That means it is very far. The edge of the wire is very far from the point P. So this is infinity, this is also infinity, this is going to minus infinity, this is going to plus infinity, and so on, right? What was our formula? The formula was P is equal to mu naught I by 4 pi sine of phi 1 plus sine of phi 2, right? So what we did there was we have fixed this angles. Okay, these angles are more or less fixed. Okay, so that's important. But what happens is, I think we have written this wrong, I guess. Just wait. Yeah, we missed out an A, right? Right. Yes. So there is an A here, obviously. Mu naught I by 4 pi A sine of phi 1 plus phi 2. So we know that if you're basically considering any particular point here, let's say this is the center joining, and any particular point here, for the finite part, this is my phi 1 and this is my phi 2. But if it's an infinite length of wire, that means this part or this angle that we have is getting straighter and straighter. Okay, it can get maximum straight up to this particular point. So a good way, okay, a good way to assume would be that this will, if we are considering an infinite length of wire, that means at a very far distance, this will become almost straight, this will become almost straight. That means the angle that it will make on this side will be 90 degree, and the angle that it will make on this side will also be 90 degree. So that means if you're basically considering for an infinite length, okay, infinite length, this phi 1 and phi 2 would be equal to 90 degree. Okay, so that means the magnetic field that we are going to have is mu naught I divided by 4 pi a into sine 90 plus sine 90. So that would be 2 into sine of 90 degree, right? So sine 90 is 1. So we can just take this to be mu naught I by 4 pi a into 2. I can cancel this out. This is 2. This is mu naught I by 2 pi